Last time we had very fancy gradients representing our running applications. After about a week of work and roughly 2,000 lines of code, now we have solid rectangles. Wait, what? Okay, so it might seem like we've regressed, but these solid rectangles are a lot more advanced than they might look at first sight, and I've got a few demos lined up that'll hopefully showcase that. Let's take a closer look. We'll be building up a Wayland client alongside our compositor to better isolate and understand the individual protocols. To make this a little bit easier, I've gone ahead and pulled out some of the generic utilities from our compositor into a separate Meson module. For now, this includes our logger and linked list, but we'll be expanding on this later on. This allows both our client and our compositor to make use of them. I also did similar for our two test frameworks, Unity and FFF. We'd created this test client last time. It didn't do much, it just connected to our compositor and maintained that connection until it received a signal to exit. It does a bit more now. So in order for our client to submit Wayland requests to our compositor, the first thing we need to know is what capabilities our compositor actually has. Basically, which interfaces it's implemented and registered as Wayland globals. On our initial connection, the compositor's registry broadcasts its list of globals. So what we need to do is add a listener for those events that appropriately handles them. All those details aside, that's this function here. For the sake of debugging, we're going to have it print each global, though there's only a few of them we actually care about. Those few that are important to our client, we can save off references to inside of our client's global state. That way we can access them anytime we need them. Let's go ahead and compile our project. Run the compositor and a client, and then quit out of them. When we check out our log files, we can see the name of each global is getting printed. The three globals that we're saving off to make use of, which are all related in some way to displaying a client on the screen, are Wayland shim, Wayland compositor, and XDG WM base. All of the Wayland requests and events that we're going to be working with in this specific video extend from one of these three global interfaces. Starting with Wayland shim, which stands for shared memory, this is what allows our clients to allocate a buffer of pixel data in memory, write some colors to it, and then share that buffer with the compositor for getting displayed. There's a Wayland shim pool resource that each client's going to create from our Wayland shim global. The pool is the actual allocation of memory, but to make it useful, the clients will then need to create one or more Wayland buffers from each pool. Next, we have Wayland compositor. Clients can create two types of resources from this, Wayland surfaces and Wayland regions. The Wayland surface is the star of the show today. It represents a rectangular area on the screen that displays something. Surfaces might seem a bit redundant with buffers, but if you think of them like a wrapper around the buffer for metadata, then they'll make a bit more sense. Not only do they track what buffer to display, but they also track things like negotiations about the surface's size on the screen, the areas which are opaque versus transparent, the areas which are capable of accepting user input, the areas on a surface that have been damaged, which is a fancy way of saying in need of a redraw, and a few other things. Many of these are just optimizations, which we're not going to make it to today, but I wanted to at least mention their existence to help distinguish between surfaces and buffers. You might have noticed that much of that metadata was about tracking areas within a surface. For example, the areas which are damaged. That's where the Wayland region comes in, which is basically just an X, Y, width, and height that identifies a rectangular area within a surface. Again, we're not going to be making it to regions today, but they'll become relevant in future videos. Okay, so the last global that's going to come into play today is XDG WM base. You might have noticed that this doesn't start with the usual WL prefix, and that's because it's a Wayland extension created by XDG, and it ties closely into surfaces. In order for a surface to actually be used, it needs to be assigned a role so that our compositor knows how to handle it and what capabilities it has. There's a lot more on the screen than just an application window. There are also mouse cursors, pop-up and context menus, and a few other less common things. And while it might make sense for an application window to be made full screen, I can't really say the same for context menus or mouse cursors. The XDG WM base global creates an XDG surface that's tied to our Wayland surface, and that allows the surface to be given either the XDG top level role, which is for an application window, or an XDG pop-up role for pop-up menus. Again, there are some other roles a surface can take, but those are for another video. Today's main focus is going to be on XDG top level. Let's say we want our client to create an application window. How would it go about doing that? Well, it starts off by making a Wayland surface, then an associated XDG surface, followed by giving it the XDG top level role. So we have a top level, but we still can't use it just yet. It needs to go through an initial configuration sequence that negotiates its size with the compositor. I'm not going to cover all those details here, but the process goes something like this. The client starts off by saying, "Hey, I'd like to be rendered." Then the compositor replies, "Okay, the biggest you can be is 1920 by 1080, but I only want you to be 1024 by 768. You get all that?" Then the client responds, "Yep, got it. I made a memory pool that can fit two 1024 by 768 buffers. I've also created those two buffers. Here's the buffer I want the surface to show first. It's ready whenever, by the way. You can go ahead and show it, please." Then the compositor ends the exchange with, "Okay, I've recorded the buffer contents. Feel free to go ahead and reuse it." Let's take a quick minute to talk about shared memory and our pixel buffers. First of all, using Wayland shim is not the most efficient for computers that have graphics cards. There's an entirely separate protocol called DMA buff that uses graphics memory rather than standard RAM. But it's supposedly a lot more complex, so we're going to go ahead and just fall off that bridge when we get to it. I'd mentioned that we create two buffers. Our client's going to do double buffering, which basically means it can write an image to one buffer, while the compositor is reading and rendering the other. When the compositor is finished with its buffer, the two buffers just swap places and the process repeats. This takes a little extra memory, but it greatly simplifies our code working with the Wayland API, while also reducing the delay between frames being ready. The pixel buffer itself is basically just a really long array of 32-bit integers, with each integer representing a pixel. We'll be using hex formatting for hard-coded numbers in our code to make our colors a little more readable. If I were to write this number in my code, you'd be like, "What?" But if I write this hex representation, that's a bit more readable as white. Just like this number probably doesn't mean red as much as this one does. Now that we're all subject matter experts on pixel buffers, let's go become artists and draw a few things. I showed you the solid rectangle earlier, which was probably the most earth-shattering thing you've seen so far in this video. When our client starts up, the color we display is actually randomly chosen, which makes the clients a little more distinguishable between each other. Let's also try randomizing their position and their size. Too many colors. Here we have the for loops in our client code that actually fills our buffer with that solid color. These boxes are supposed to represent applications, so how about we help sell that idea by giving them a border? To do that, we're going to edit the loops, making the color white for any pixels near the edges of the buffer. And what about a title bar at the top? I mean, it's fake, doesn't do anything, but that's okay, still looks neat. One more fun thing to add, let's put a circle in each client, using a different color which is also randomly generated on startup. For now, we're just going to put it in the center of the buffer and give it a predefined radius, but in future videos, I've got a few plans for making more use out of this circle and all of its wonderful roundness. But again, that's for later. If you've been sitting there trying to find holes in my explanation of all this, you've probably been screaming at your screen for at least a few minutes now. There's one gap that I haven't actually explained yet, and that's how the compositor goes from receiving the buffer to actually showing it on the screen. As of now, we're just committing the initial frame and then never updating or committing anything ever again. I'm going to leave updating and animating frames for a future video, as there's a bit of work involved to synchronize the frames correctly with your monitor's refresh rate. But we can take a look over at our compositor's commit request handler. When it receives a commit that had a buffer attached, at the end down here, it converts that buffer into an OpenGL texture before scheduling a new render on the screen. You can think of a texture as basically just wrapping paper for some shape. It contains some picture or pattern, and on its own, it's entirely useless. So to actually view a texture, you need to wrap it around the surface of something. We're just working with 2D shapes, and in the case of our surfaces, they're specifically rectangles. There's no back of the shape or anything that we have to wrap our texture around. It's just the front surface. So that's how we get the client's buffer onto a rectangle for being displayed, but how do we give the rectangle the correct size and position? I'm going to let you in on a little secret. All of our surfaces actually share the exact same rectangle in OpenGL. It's a unit quad, which basically is just a square with an xy of 0, 0, and a width height of 1, 1. But for some reason, I'm able to give them all different sizes and positions on the screen. They're not all smooshed into the upper leftmost unit. What kind of witchcraft is this? Do you remember back in school when your math teachers were giving you a bedtime story about matrices? And you were probably all like, yeah, but when am I actually going to use this stuff in the real world? Well, the answer is today. I'm using projection matrices to map our 1x1 unit quad to the size and place the surfaces should be on the screen. Since it's projecting a surface, I call it the surface projection. There's also an output projection somewhere else that maps our OpenGL canvas into the right size and position for our particular monitor. I created this utility function which populates a projection matrix. These two numbers adjust the position on the screen, and these two adjust the scale. And this final 1 was probably explained in a class that I fell asleep in. In our shaders, this matrix gets multiplied to each of our surface's vertices, so each of the 4 points that make up a rectangle, and that gives us its location within our OpenGL canvas. Our surface projection is created here when we try to render the surface. Just for fun, let's try doubling the scale of our surfaces. This should make our surfaces twice as big. Yeah, that looks about right to me. Then for our output projection, the one that maps our final OpenGL canvas out to our monitor. That's created here. Let's adjust the Y position and vertical scale to flip our output upside down because, you know what, that seems like an incredibly useful thing to do. Okay, enough nonsense. Let's wrap this up. So there's still a lot of work for us to do, but we'll get there. Next video is going to be continuing on with surfaces, but there's a few different directions I can go. I'm not sure which it'll be yet, so I'm going to leave it a little vague for now. But hope you enjoyed this video, and I'll catch you in the next one.